Welcome to today's Brown Bag webinar in science. My name is Aldo Rosales. I'm the Research Administration and Program Assistant here at ACSM, and I'm with Lynette Kraft, our Chief Science Officer here. This month, we are pleased to welcome Dr. Paul Nagelkirk as our presenter. I'll tell you more about Paul in just a minute. First, if any of you are experiencing difficulty seeing or hearing the webinar, please log off and back on. It is most likely due to your internet connection. Paul will present for 25-30 minutes, and then we will have 15 to 20 minutes for answers after his talk. If you have questions during his presentation, please type your questions into the question area on the GoToWebinar screen. Now, here's a bit about Paul. Dr. Nagelkirk is the Director of Integrative Exercise Physiology Laboratory and an Associate Professor of Exercise Science at Ball State University. He received his Ph.D. in Kinesiology from Michigan State University. He's a past president of the Midwest chapter of ACSM and was recently named a fellow of ACSM. His research interests generally focus on the influence of exercise on molecular mediators of cardiovascular diseases, with a particular emphasis on blood coagulation and fibrinolysis. At this point, we will turn it over to Paul.
We had to give Aldo one hard word to say. So welcome, everybody. This is Lynette Kraft. We're going to turn it over to Paul now.
Great, thank you. Let's see. Let me click show my screen. Can you all see me now, Lynette? Am I good?
Yep, we can see it.
Very good. Thanks for that introduction. As Aldo said, my name is Paul Nagelkirk, and I do have interest in coagulation and fibrinolysis. And so I'll just briefly talk through some of the ins and outs of hemostasis and some of the work that we've done over the years in this area. So just in general, this is what I've laid out for today's presentation. I figure it makes sense, what I'm calling hemostasis 101, because this is not a physiological system that we talk very much about in exercise science classrooms. So we'll cover some of the basics of these processes, and we'll describe how hemostasis typically works in your favor as the hero of the cardiovascular system, but how sometimes it can also be the bad guy and it sometimes creates problems for us. And then we'll talk about some of the research that's been done about how hemostasis adapts to regular exercise training. And we'll talk about how acute bouts of exercise will influence some of the proteins that are involved here. And then at the end, we'll talk about some of the work that I hope can get done in the upcoming future. So first of all, hemostasis comes from this fancy Greek word that basically means to stop or interfere with blood flow. And in the research that we're doing now, we're primarily referring to a blood clot, which forms a solid mass, and that can either slow down blood flow or even in extreme cases stop it altogether. And the process of hemostasis is a pretty sophisticated and complex one, and it involves several different steps. And I don't want to get too deep into the weeds, but I figure we'll just cover the basics. First of all, hemostasis, or the formation of a blood clot, it typically starts with the work of platelets. And platelets are little cells. You have several, or at least 150,000 or so, that are floating around in your bloodstream at any given time. And platelets react to injured blood vessels. When they see a blood vessel that's been damaged, they first of all are attracted to the site of injury, and they will adhere themselves to the damaged part of the blood vessel. And that adhesion triggers a response where they become activated, where they will quite literally change shape and flatten out. And that also creates some biochemical changes that leads to some surface receptors showing up that makes the platelet sticky. And it's then able to be aggregated with other platelets. So essentially what happens is a platelet will become activated and will recruit other platelets to the site of injury. And before long, you get this clump of platelets that have all glued themselves to each other, forming what we typically refer to as a platelet plug. And with a small injury, a platelet plug is probably adequate to completely stop the bleeding and allow healing to happen. But the problem with the platelet plug is that it's a little fragile. So larger injuries would then require the help of the next phase of hemostasis, which we call secondary hemostasis. And this involves the work of the coagulation cascade. And the cascade is a series of enzyme reactions. What you're seeing on the screen here, all these Roman numerals, they represent different enzymes, which we refer to as coagulation factors. Later on in the presentation, you'll hear me talk about factor VIII and factor VII, and I'm referring to the proteins that are part of this process, where it's literally one enzyme activates the next one, which activates the next one, and the next one, and ultimately what we're all doing is working to create fibrin. And fibrin is a molecule that, when it is formed and starts to glom together with other fibrin molecules, it creates this net-like construction that allows it to then trap other cells and platelets, and it ultimately forms this very sophisticated, dense plug that then covers up the injury and theoretically prevents blood loss from happening. Now, the next phase is sometimes referred to as tertiary hemostasis, but in reality, it's kind of the next phase, because once the fibrin clot has done its job and stopped the bleeding and allowed healing to occur, we don't want that fibrin clot to hang around for forever. It's a solid mass. It can interfere with blood flow, and so we need that to then be dissolved and disposed of. And the molecule that does that is called plasmin, and plasmin it literally dissolves fibrin into smaller little proteins that you can then clear through the liver. And plasmin, in order to do this, it must become activated. And this is the key to the whole operation. The activation of plasmin is done by a family of plasminogen activators. And so the blue molecule you see here, I'm gonna try to point on my screen. This guy right here, TPA, stands for tissue plasminogen activator. And this is a molecule whose job it is to activate plasmin. This is the rate limiting step of what we call fibrinolysis. So TPA is something that we measure in the blood, and the more TPA you have, the more we know that you are prepared to dissolve fibrin blood clots. Now, TPA has its own arch enemy, and there's a family of plasminogen activator inhibitors. So what you're looking at here, this is PAI1, we commonly refer to it as PI1. This is plasminogen activator inhibitor, and it binds with TPA and prevents TPA from then from activating plasminogen and then dissolving the blood clot. So PI1 is inhibiting the process of dissolving the fibrin clot. The more PI1 that we see in your bloodstream, the more likely it is that you would then retain the fibrin that's there. So the hemostatic system or systems in most cases under healthy conditions is the hero, because if you experience an injury and if it's substantial enough that you damage one or more blood vessels, the concern is that you could then bleed out. And frankly, you don't have a whole lot of extra blood to go around. So this is a potential serious problem, but a healthy coagulation and fibrinolytic system will then react to start the process of stopping the blood loss, activating the coagulation cascade, which then finishes the whole thing, creating this very nice, stable blood clot, preventing blood loss from happening. And then fibrinolysis, the third wave here, is ordinarily delayed to allow the bleeding to stop, but then the timing is just right so that those plasminogen activators later jump in to start the process of dissolving fibrin. Now that it's done its job, we can dispose of it. And oftentimes in the literature, we read about keeping a proper balance between coagulation and fibrinolysis. Having the right amount of both things allows you to prevent blood loss, allows you to create healing opportunities, and then later on allows for the appropriate disposal of those proteins that have finished the job. That's the good news side of the hemostatic systems. Unfortunately, hemostasis sometimes is the bad guy, because if a blood clot forms in an artery that we don't want a blood clot to form, and most often we're talking about a coronary artery or a carotid artery where this happens, and if it blocks up the blood flow, if that blockage is bad enough, it can literally prevent oxygen and other important nutrients that are supposed to be delivered in the blood from being delivered to living tissue, and that can lead to tissue death. And the animation you're looking at here is obviously a heart attack. So this is the thing, the vast majority of the heart attacks that happen are caused by a blood clot. The vast majority of strokes that happen are caused by a blood clot. And there's nearly 1 million thrombotic events that are going to happen each year, and that includes pulmonary embolism and deep venous thromboses. So ultimately, we're looking at, more than 2.5 million blood clot related events that happen every year. So this is a pretty big problem in terms of our cardiovascular health. And furthermore, blood clotting is connected to a whole slew of chronic diseases, and the obvious ones are the cardiovascular diseases, but it's also implicated in diseases like diabetes and cancer, some chronic conditions that you might not automatically assume are related to impacted hemostatic systems. So the table you're looking at here, this pulled from a review paper that I'll talk about later on, where generally speaking, people who have heart disease, we know they typically exhibit elevated levels of coagulation potential. They're really good at making blood clots. And they typically have a reduced level of fibrinolytic capacity, meaning they don't have the balance that I was referring to a minute ago. They're not great at dissolving blood clots, but they are good at making them. So this is the ugly side of the hemostatic systems. Now, we know that exercise is good for you. Hopefully you all knew that. Exercise is good for you. It's heart healthy. And one of the reasons that we think, especially aerobic exercise training, is heart healthy is because of how it influences these hemostatic processes. So this is the review paper I was referring to a second ago. This came out a number of years ago now, but it just summarizes a lot of what's been published with regard to the hemostatic systems, what we know about how exercise influences them, not only in healthy individuals, but also in people who have cardiovascular diseases. And generally speaking, we are of the opinion that regular exercise training leads to a reduction in coagulation potential. So this would be considered a reduction in the risk of someone having a heart attack or some other adverse event. And related to that, we also see that exercise training leads to an increase in fibrinolytic potential. So those two primary proteins I talked about, TPA and PI1, they are affected by regular exercise training. Now, most of the research that's been done in this area is focusing on traditional moderate intensity exercise training. And to be completely honest, let me flip back. To be completely honest, the literature is a bit equivocal on this. It does not consistently show that moderate intensity aerobic exercise improves coagulation or fibrinolytic potential. So there's a lot more that needs to be done on this. And this includes, honestly, even earlier work from our own laboratory where we failed to consistently show that regular exercise training leads to consistent improvements in these proteins. So there's some things that need to be done. One of the questions that we had was that maybe the issue is related to the moderate intensity. We are so good at following ACSM guidelines that we want all healthy adults to participate in regular moderate intensity exercise. But maybe if we did a different kind of exercise, we might see more consistent improvements in hemostasis. So we recently completed a study where we did, instead of moderate intensity work, we went ahead and did high intensity interval training. And this was a little bit different. We theorized that the high intensity work would maybe provoke adaptations that we don't consistently see with moderate intensity stuff. And just here's a little teaser. Later on in the presentation, I will discuss the acute exercise responses, and I'll just let the cat out of the bag. Acute exercise responses are dependent on intensity. The higher your intensity of exercise, the more we see some responses. So theoretically, we thought maybe high intensity regular exercise training might provoke adaptations in ways that we don't consistently see with moderate intensity work. So we designed a study, we recruited, and we're actually able to retain 21 men who willingly came to our lab for 8 weeks. And for 3 times a week, they participated in repeat Wingate training. And for those of you who are familiar with Wingate exercise tests, it is a maximal intensity cycling protocol, very, very high intensity, high resistance. And what we would do is a Wingate bout, 30 seconds of high intensity cycling, and then 4.5 minutes of active recovery, and then we would do another Wingate. So It started out with 3 repeat Wingates, and over the 8 weeks, we progressed up to 6 repeat Wingates. And what we found is that it didn't do anything to fibrinolysis. So the fibrinolytic profile, which we consider to be cardioprotective, the more fibrinolytic activity we see, the less likely you are to experience a clot-related adverse event. So we were a little surprised that we didn't see any adaptations with the fibrinolytic proteins. With coagulation, we took a number of measures that also showed no effect of the training, including TAT stands for thrombin antithrombin. Thrombin is one of those proteins of the coagulation cascade. It's actually the rate limiting step of the coagulation cascade. We also took measures of fibrinogen. This was another part of the coagulation cascade, and we observed the following adaptation. First of all, we took a 4-week measurement here just to sort of capture the time course of any adaptations that we might see. And we found that fibrinogen levels significantly dropped over the first 4 weeks of training. But that decrease in fibrinogen was completely undone in the second half of the study. So the last 4 weeks of training, we saw a significant increase in fibrinogen levels. So the explanation for this, there's 2 possible explanations. One is that what we're seeing is related to coagulation activity. However, we didn't see any other coagulation adaptations, so that further led to the consideration of the fact that fibrinogen, in addition to being an important part of the coagulation cascade, it's also what we call an acute phase reactant. It plays a role in inflammation. And what we think might be happening here is that in the last 4 weeks of our training, where the participants were doing not 3 or 4 repeat Wingates, they were doing 5 and 6 Wingate trials back to back to back. The volume of training in the last 4 weeks was substantially greater than what we had in the first 4 weeks. And so we speculated here that some of this was related to the fact that we might be inducing inflammation with a high volume of really, I'm not gonna lie, butt-kicking exercise training. And I can say that as one of the participants in this study. So the ultimate conclusion from this, and this is a paper that is in the final stages of review, we're not entirely sure if we're seeing coagulation adaptations here, but instead I kind of think that what we're seeing is an inflammatory response. And in the last 4 weeks, we were seeing inflammation being induced because of the high volume of training. Another issue, like I said earlier, that we are, most of the research is done on moderate intensity aerobic exercise. There's really very little that we know about how strength training influences hemostasis. So this was a study that we literally just finished in the past year, and we'll be presenting the results of this at the upcoming ACSM annual meeting. Up to this point, there's just a couple of cross-sectional studies that have been done. And to be honest, the results of those studies are contradictory to each other. One study suggested that people who are resistance trained have a higher fibrinolytic potential than people who are not strength trained. And then another study basically reversed that and said that people who were resistance trained had a lower fibrinolytic capacity. So clearly there are things we don't know about this. And so we designed a longitudinal training study, and we enrolled 16 men and women who came in and worked out 3 times a week for 8 weeks. This was a full body strength training program. I think there were 8 different lifts we had them do when they were coming in. All of this supervised by a team of high qualified and ambitious grad students, thanks to those of you who are listening. What we observed was that strength training did not change coagulation potential. And we had several different measures that we took, some parts of the coagulation cascade, and these little APTT and PT that I'm showing here. These are measures of clotting time. This measures the activity of the entire coagulation cascade. So we really didn't see a whole lot of anything with regard to coagulation. And with regard to fibrinolysis, TPA, this was the activator of fibrinolysis, was also not influenced. But we were pretty excited about this. We saw these are 2 different measures of PI1. So again, PI1 is the inhibitor of fibrinolysis, And so when Pi1 goes down, we consider this to be a beneficial thing, meaning you are less likely to inhibit the dissolving of a fibrin clot. So this is a good thing. And what we're looking at over here on the left, this is active Pi1. This refers to Pi1 molecules that are not currently bound to anything. And we see a significant reduction in active Pi1. And over here, we see total Pi1. This is including Pi1 molecules that are free to do something and those Pi1 molecules that are already bound to a plasminogen activator. And again, it went down, significant reduction in Pi1. So this supports one of those cross-sectional studies that I mentioned a second ago. And ultimately, we view this as a really important cardiovascular adaptation. And this is something that is relatively new. I'm hearing more and more people talk about, more scientists who are insisting that we need to learn more about cardiovascular adaptations to strength training. And this would certainly fall into that category. Mechanistically, we're not entirely sure what precisely we're looking at here, but we speculate that part of this adaptation is related to the changes in lean body mass that you get with strength training. There is a small amount of evidence that suggests skeletal muscle plays a role in producing and secreting these proteins. And so we think adding to your lean body mass might make it possible that we're changing some of the hemostatic profiles because of the way skeletal muscle influences these things. Let's shift gears now. We'll talk about how acute bouts of exercise influence some of these measures. And the literature on this front is much more conclusive than it was with respect to training adaptations. We know that blood coagulation activity goes up significantly when you exercise. The likelihood of you making a blood clot goes up quite a bit while you work out. And at the same time, we see increases in fibrinolysis. So that balance that I was talking about is definitely evident during the acute exercise response. The increase in fibrinolysis is viewed to be as offsetting to the increase in coagulation. But as I mentioned earlier, this is probably intensity dependent. This is a study that was done by some good friends years ago, where they explored the effect of aerobic exercise intensity specifically on fibrinolysis. And so they were measuring TPA and Pi1 during exercise that is above lactate threshold intensity and below lactate threshold intensity. And credit to these investigators, it was a well-designed study, well-controlled. They controlled for energy expenditure. So they had two separate bouts of exercise, one that was above the lactate threshold, and the participants sustained this for about 20 minutes. And that was wound up being at a roughly 77% of their VO2 max. And then the below lactate threshold trial was at about 41% of their VO2 max. And they calculated how many minutes they would need to complete in order to burn the same number of calories. And what they observed was that, first of all, TPA activity only went up during the trial that was above lactate threshold intensity. So active TPA was not affected by below lactate threshold. Now, Pi1 decreased whether you were above lactate threshold or below, but the increase, or excuse me, the decrease in Pi1 that was observed in the higher intensity trial, significantly greater than what we saw in the lower intensity trial. So clearly the intensity of acute exercise plays a role in how much we would expect fibrinolysis to change. More recently, this is a paper that got a lot of attention. This is kind of a new thing for me. It was a study idea we came up with because it was going to be quick and easy to do. I had a couple of grad students who wanted to pursue this, and it wound up being far more interesting than I thought it was going to be completely honest. But caffeine, let me just get this out of the way first. I love caffeine. I'm not shy about the fact that I have a pretty well-developed caffeine addiction. And caffeine has gotten a lot of attention in the exercise literature. We know a lot about caffeine, about how it affects the sympathetic nervous system, how it can induce vasoconstriction, which we think is responsible for the way caffeine changes blood pressure. There's some good evidence that says caffeine will change arterial stiffness. So there are a number of things we know about caffeine, and those things have been shown in the literature to also affect hemostasis. But no one up to this point had directly measured the way that caffeine might influence blood coagulation and fibrinolysis. So this is a study, oh, and it's worth pointing out, caffeine also pretty effective as an ergogenic aid. You'll find caffeine as a pretty major ingredient in lots of pre-workout supplements for this very reason. So this is a study that we did with some friends at James Madison University in Virginia. We pooled our collective resources, and we wanted to find out if one dose of caffeine would influence hemostasis, first of all, at rest, but also the hemostatic responses to high intensity exercise. So we enrolled a number of people, and they came to our laboratory 2 separate times. One time they were given a placebo drink, and the other time they were given a beverage that contained 6 milligrams per kilogram of body weight of caffeine. So it's a pretty big dose of caffeine. This was done in blinded fashion and in random order. And what we observed was that caffeine, first of all, it didn't influence fibrinolysis at rest or during exercise. We really didn't see any fibrinolytic changes with caffeine. With coagulation, one of the measures we measured was fibrinogen. And what you're seeing here is that fibrinogen increased significantly during exercise. We expected that, but we also saw that the caffeine didn't really change that response. So between caffeine and placebo, the increase in fibrinogen was pretty similar. But this one got a little interesting. Factor VIII is one of the steps of the coagulation cascade, and it's one that pretty consistently responds during exercise. So we like to measure this during exercise studies. And factor VIII went up during exercise. We expected that. But what you're looking at here, all the symbolism up here means 2 things. Number one, we're seeing a main effect of caffeine, meaning during this caffeine trial, we saw more factor VIII in the bloodstream than we did during the placebo trial. But more importantly, it was this time by condition interaction, which means the increase in factor VIII was greater when they took the caffeine than it was when they took the placebo. So for people who consume caffeine prior to exercise, one of the outcomes that we would expect to see is they have this increased coagulation response compared to when they would consume a placebo. So this paper in Medicine, Science, and Sports and Exercise got a fair amount of attention from the popular media, and I kind of had to field a lot of questions from journalists who were quick to say things like, so does that mean we're going to have more heart attacks if we're consuming caffeine before exercise? And I had to kind of calm that down a little bit. The long and short of it is this: one dose of caffeine increases coagulation potential without a similar increase in fibrinolysis. This is referring to an imbalance between coagulation and fibrinolysis. And so potentially I can see how a journalist would jump on this and say, ooh, does that mean we're going to induce more heart attacks? And the answer to that is maybe. There are potentially implications here for an adverse cardiovascular event, but more importantly, let's just take a beat and think about this. Because first of all, exercise is safe. It is a low risk endeavor for most people. Secondly, caffeine is safe for most people. If you are currently enjoying caffeine before a workout or just throughout the course of your ordinary day and you're experiencing no negative outcomes because of that, this study is not a reason to stop that. I would suggest that for people who have a diagnosis of a chronic illness that we know leads to increased risk of blood clotting, those people might think twice about consuming caffeine before exercise. Or if it's someone who has lots of cardiovascular risk factors, cholesterol, blood pressure, age, things like that, those people might reconsider the wisdom of using caffeine as a pre-exercise supplement. For everyone else who is healthy and not at risk of an adverse event, this is probably not a reason for concern. So there's much to be done on this, and I, like all of the other webinars that I've seen with this ACSM program, there's much more work that needs to be done in this area. There are very few people who are studying hemostasis as it responds and adapts to exercise. So here are just a few of the research questions that I would hope we can answer in the not too distant future. First of all, I really want to find out more about how exercise training leads to adaptations for some people, but not others. And part of that is I want us to study more people who are not healthy. It's convenient and easy to enroll healthy people into an exercise training study, and that's all well and good, but there's much, much more that we can learn from studying people who have diabetes or cancer, or people who are obese or have cardiovascular disease. I also would like to explore some different types of training regimens. So I mentioned our high intensity interval training study. I'd like to do that again, maybe in a different population, but there are some other types of training that many people are currently pursuing. Blood flow restriction is an example of one for strength training that some people are experimenting with. That's produced some pretty interesting findings in the literature. And I'd kind of like to see what that does with hemostasis. I'd like to explore some other nutritional supplements. That caffeine study was fun. And there are some other nutritional supplements that have been identified in the literature as potentially affecting the hemostatic systems, including creatine is one of them. And then finally, I would like to know more about the mechanisms. There really needs to be more mechanistic work in this area. You know, I mentioned that skeletal muscle, there's some evidence that skeletal muscle could modulate some of the adaptations and responses that I've highlighted today. So there's more to be done on that. I would like to know more about how liver blood flow affects this. The liver is a source of production and also clearance of a lot of the proteins that I've described today. And we know that liver blood flow is likely affected during exercise, but a lot of these dots have yet to be connected. So this is just a small window of the type of work that I hope can be done, at least during my career, and hopefully I can get more people involved in this. So with that, I'm going to turn the presentation back over to Lynette. If there are any questions, I'd be happy to answer them now.
Great, thank you, Paul. That was really interesting. First, we want to remind everybody who's watching the webinar, please enter your questions into the GoToWebinar screen. We would love to hear your questions. We're going to start with a few questions from the national office to give people time if they didn't already. Paul, if you can turn on your webcam, go for it. If not, that's okay. Anywho, I'm going to start with a question. Several of us here are wondering, are there differences between men and women in this, or are there different hormones between the two sexes that might play a role? And we can see you. That's great.
I'm sorry about that you can see me now. Now, to answer your question, yeah, there's definitely sex differences in this, and the sex-specific hormones do play a role in this. So anytime we do studies with women, we have to be careful to control for phases of menstrual cycle. Generally speaking, women are thought to have lower risk of coagulation compared to men until menopause. After menopause, women typically start to look more and more like men, hemostatically speaking, and a lot of that is related to the hormones, the estrogen and progesterone in particular. So that's the short answer to that. There's definitely a sex-related response to this.
Great, thank you. I'm going to ask a really selfish question. I had a stroke this summer, so I am familiar with TPA and blood clots and breaking them down. I'm curious, has there been any research on the relationship or the interaction between exercise and medications that folks would be taking follow an event, whether it's a statin or other type of medicine that would affect platelets?
No. And what a great thing for someone to do, Lynette. Yeah, no, there's so much we don't know about this, the interaction between exercise and medication. And I think this is true for not just hemostasis, but there's so much we don't know about how exercise might modulate the effects of a particular medication. So the shorter answer is no, we don't really know. We understand that the medications are beneficial for you. We understand that exercise is beneficial for you. We don't fully understand how one might influence the other.
Thank you, Paul. Next question we have here is, what is the catalyst, if there is one, for activating secondary hemostasis?
The catalyst, one of them is platelets. So one of the things that platelets will do is when I refer to the step of activation of platelets, that will actually lead to the activation of the coagulation cascade. And then there's some other things that can be external, like an injury will stimulate the activation of the coagulation cascade. One of the, I'm not going to flip back to that coagulation cascade slide, but if you go back there, you'll see a TF that stands for tissue factor. And that's one of the things that we see is implicated in an injury kind of a situation. So there isn't one individual catalyst. There's any number of them. So including the platelets, including the injury, we can simply do things like rub an endothelial cell, like by increasing vascular shear stress, which is something that we see during exercise. That can provoke some of this stuff. So the cool thing about the coagulation cascade, it's so complex and there's so many players in it that you can literally activate the process at really any step along the way. So all those Roman numerals, all those coagulation factors, any one of them can be activated, and that will ultimately lead to fibrin formation. So it's a large number of things that can stimulate the coagulation cascade.
Thanks for that. Next question we have here is, what was the TPA response to strength training?
There was none. It did not adapt in any way. So as far as training adaptations go, their TPA didn't change and Pi1 didn't change. It was very, very flat. I didn't talk about acute strength training. There's some other work that's been done looking at simply individual bouts of strength training. And the responses that we see during one bout of weightlifting are quite similar to what we see during aerobic exercise. So during a single bout of strength training, TPA would go up, Pi1 would go down, but we don't see any adaptations with regular strength training.
Thank you. So in the terms of future research, would it behoove the researchers to account for body composition, or can we expect to see differing results in the terms of fibrinogen content post-exercise, depending on blood flow or body fat percentage or muscle mass?
Yeah, I think that's a great observation. So, the strength training study, one of the outcomes that we're speculating is that it's related to lean body mass, but it's also worth pointing out that the literature suggests that obesity influences these things as well. And, ACSM limited me to only 25 minutes on this. I could have gone way longer if y'all would let me talk about all the things I wanted to talk about, because we had a study where we looked at women, and it was the fibrinolytic responses to acute strength training. And we observed that the women with higher body fat percentage had a different profile than the women who were leaner. So it's not just lean mass, it's also body fat that influences these things. And so controlling for body composition is something that honestly should get a lot more attention in this type of literature.
Okay, Paul, it's Lynette again. So is there any difference, I assume there's not, but is there any difference in these cascades, whether it's a DVT or a PE or a cerebrovascular event? I assume that the cascade that leads to this is all the same.
It is all the same, and it's basically all about fibrin blood clots, but it's simply a difference of where they are formed and where they travel to. So blood clots that are formed in arteries create different outcomes than blood clots that are formed in veins. So a blood clot that's formed in a vein, the concern is that could travel to the lungs, and then we have pulmonary embolism, and that can create some problems. Risk of death. Blood clots that are formed in arteries, that's less of a concern that they'll make their way to the lungs. The bigger concern is that it would form in a carotid artery or a coronary artery and create a stroke or a heart attack. So the processes are the same. It's just simply where they take place.
And is there any difference in these cascades or these responses based on age. We noticed that a lot of the participants are sort of young, healthy folks. Does age influence how these things work?
Yeah, it does. It's another really good observation. So like many cardiovascular variables, we find that aging leads to a deterioration of things. And generally, the older you are, the more likely you are to have higher blood coagulation potential and probably lower fibrinolytic potential. And we think part of that is related to arterial elasticity. As we get older, the arteries become a little less flexible. That creates some vascular changes that would be more likely to provoke coagulation. So aging is a natural part of this, and this is one of the reasons why you're far more likely to experience an adverse event when you're older.
Okay, thank you, Paul. Aldo here again. We have time for 2 more questions here. So on the Wingate exercise, what was the average age of the participants?
They were young. I think the average age was around 23. I would need to pull it up. But they were, it was a bunch of men who were in the building and friends of friends. So it was a lot of students, undergrad and graduate students. So it was a mix of upper level undergrads and some grad students. So they were in their low 20s.
All right, thank you. So could you discuss some of the protocol for the study, like such as an example of the workouts for the participants completed?
Are you talking about the high intensity study?
Yes.
So the workouts, it was is literally just doing Wingate tests. And so we would have guys in the lab, and we typically would bring them in like 2 or 3 at a time and made a social event out of the whole thing. But you put somebody on a bike, and after an appropriate warm-up, they would do all out cycling for 30 seconds. And then they would have 4 minutes and 30 seconds to recover. And they could choose what they wanted to do. They would walk around the room. Some of them would choose to stay on the bike and cycle at a low intensity, but they just needed to move around for 4.5 minutes. At that point, they would do another Wingate, another maximal intensity cycling bout. And so we would repeat that pattern. For the first 2 weeks, they would do 3 Wingates separated by 4.5 minutes of recovery. Then after 2 weeks, we would add 1. So it was 4 Wingates. Then 2 weeks later, it became 5 Wingates. And then 2 weeks later, it became 6 Wingates. So it was all cycling exercise, all very short 30-second bouts at one time at a very, very high intensity.
So we're all tired just hearing about that.
Yeah. Oh, it's brutal.
So for folks who aren't used to doing this type of research, can you tell us a little bit how clotting time is assessed or measured or estimated during this kind of study protocol?
Yeah, that's a good question. So there are some standard coagulation tests that are done in a doctor's office, and so you referred to clotting time, and I had a slide where I showed APTT and PT, and these are literally assays where it's measuring how many seconds it takes for a clot to form. And so to do this kind of test, you have to have a machine that's called the coagulometer, and you typically need some reagents where ultimately we add calcium to somebody's blood sample, and that triggers the coagulation cascade, and that then is timed. So the more quickly the clot forms, the more we know that you have a greater coagulation potential. So that's one pretty standard way to do these things. But honestly, most of the science is looking specifically at individual proteins. So we like to use enzyme-linked immunosorbency assays to measure the concentration of things like TPA or factor VIII or Pi1. So the biochemistry of it is largely it's enzyme-linked immunosorbency assays, and some of the assays you can make up your own if you have the time and ambition to do so, but there are some commercially available assay kits that are also pretty good. So those are commonly how we measure these things in a lab.
Thank you for that. And thanks to Dr. Nagelkirk for a great presentation, and thank you for all for your participation today. In the next week, we will send you a recorded version of today's presentation. If you would like to view any of our previous Brown Bag webinars, you can see them at acsm.org. Click on the Learn and Develop Professionally tab, and then click on Brown Bag Series. With that, we'll end the webinar from the National Office by giving Dr. Nagelkirk a round of applause.
Thank you, Paul.
Thank you.